Hello viewers, myself Shahan Mojumdar on behalf of Science Academia. This is yet another class from Atomic Structure Part 1. We had learned about previous class which was about various atomic models from Bohr, from Sommerfield's. So we have to know that how the atomic models were developed to the quantum mechanical model. As we have learned the previous model from Bohr, from Sommerfield, from everybody, the plum pudding model, in some conclusion they were a little bit failure, but they have given the basic idea that how atomic models work, how a structure of atom basically looks like. But in the better stage or in the next stage we had to develop, and there yet another stage came where there was a developmental stage of the atomic models towards the quantum mechanical model. There was a reason of failure. We previously learned in our classes that there are four quantum number, that principal, azimuthal, magnetic and spin. There are several quantum numbers, but in this class we will learn about that middle or that intermediate stage between the quantum mechanical model and the previous Bohr's model or Sommerfield's model. So now we have to know to start the new lesson that behind every development there are statesmen. So in this lesson there was two statesmen. One, electron have dual nature. One look like particle, another look like wave. So in our previous class we have learned for wave and photoelectric effects that wave have lambda, that is wavelength, frequency, and there is yet another equation that was later discovered or later given by de Broglie. We will learn about that for wave. For particle, that every particle has a particular momentum. We can designate the momentum as P. We everybody know that momentum is the product of mass and velocity, that is P equal to mv. After that, de Broglie derived a wave equation. From that we can get a relation of mass and velocity or from the wavelength or from the lambda value. So de Broglie give the equation that lambda equals to h by p, where h equals to Planck constant and p is the momentum, or we can say that h by mv. Now we can calculate the value of mass or velocity, anyone, from if we are given with a lambda value. Like we can give an example. A photon that have a wavelength of 4 angstrom. A photon, the lambda value 4 angstrom. So now we have to calculate that what is the mass of the photon. So before starting the calculation we have to just generalize the lambda value. As we know the lambda 4 angstrom, that 1 angstrom is equal to 10 to the power minus 10 meter. We can convert 4 into 10 to the power minus 10 meter. We are calculating it by SI unit. So we have to take the velocity as 3 into 10 to the power 8 meter per second, and the h or Planck's constant value 6.626 into 10 to the power minus 34 joule second. The later we will know about what does the joule comes from. So now if we calculate lambda h by mv, m equal to h by lambda v, or 6.626 into 10 to the power minus 34, 4 into 10 to the power minus 10, that will be below at denominator, and the velocity will be 3 into 10 to the power 8 meter per second. So finally there will left a unit of kg. how it will come? Basically joule is kg meter square per second square. So if we generalize the term of joule second, we will have a last unit kg, and the value it will be 5.5 into 10 to the power minus 19 kg. So now this is the value of the question. So we can calculate the mass. Just take a gap. The calculation will be a final value. We can calculate that. So there will be 5.5 into 10 to the power minus 33 kg. This will be the final answer. So from this question we can understand that how to calculate the mass from a lambda value. The next thing was Heisenberg uncertainty principle. So basically we can understand that what does the uncertainty means. Uncertainty means, so what does Heisenberg stated in 1927 that there is an uncertainty of position and momentum. We cannot calculate the position and momentum simultaneously for an electron or the similar like element. Like it is called uncertainty. We cannot calculate the position, that is the uncertainty of position, that is delta x, and uncertainty of momentum, that is delta p, as well as the velocity is inbuilt here. We cannot calculate or cannot estimate the value simultaneously. It was previously confused by physics observer effect. In physics, observer effect stated that we cannot estimate a system until we can change it. So if we can change, we can estimate the value easily. So now from this observer effect, Heisenberg developed the final equations. That was delta x is greater than into delta p is greater than equal to h by 4 pi. That is the final equation from Heisenberg. But this postulate also have such a limitation that this is eligible for only microscopic element. We can say for microscopic it is eligible, for macroscopic it is not eligible, because delta x, if we can take delta p at the right hand side, if delta p, if the mass is so much greater, delta x will be so much smaller. So a smaller value of uncertainty we can avoid easily. So it is eligible for microscopy. If the value or if the particle is microscopic, the delta x value will be larger, and where the uncertainty value will be larger, it will correctly eligible the Heisenberg uncertainty principle. The second thing was, any atomic model could not stated that where does the electron rotate, and it is correctly, it also omits that electron doesn't move a definite shape orbital or a perfect trajectories. So now this was the Heisenberg uncertainty principle. We will just show a calculation of this law or this principle. So basically in Heisenberg uncertainty principle, this type of mathematics come from this chapter or this formula, that a particle is moving with a mass of 5 meter per second. So I repeat, a particle is moving with 5 meter per second, and it has an uncertainty value of velocity 4%. That is velocity uncertainty value 4%. And the particle have a mass of we can say that 4 picogram. Now we have to calculate the position or the uncertainty in position. So how will you calculate it? At first we have to calculate from the mass and velocity. What does we have to calculate? The momentum. So how will you calculate it? Basically, the uncertainty of velocity can be written as delta V, which is 5 into 4 by 100. That is nearly equal to 0.2 meter per second. So that is uncertainty in position. Now, if the mass is 4 picogram, we can convert it towards kg because we are calculating in SI unit. So 4 picogram is 4 into 10 to the power minus 15 kg. So this is the conversion. Now we have to calculate the delta P value. Delta P or uncertainty of the momentum is equal to m into delta V, that mass into uncertainty of velocity. We have estimated the mass 4 into 10 to the power minus 15 and the velocity uncertainty 0.2 in meter per second. So it will be 0.8 into 10 to the power minus 15 kg meter per second, or 8 into 10 to the power minus 16 kg meter per second. So we have also calculated the momentum. Now from the uncertainty of momentum we can take the formula delta x into delta p is equal to h by 4 pi. When we are calculating such a question or we are solving such a numericals, we have to take the equity value. So now delta x equal to h by 4 pi into delta p. So we can generalize the value h 6.626 into 10 to the power minus 34 joule second, 4, and the pi value is 3.14 and delta value is 8.8 into 10 to the power minus 16 kg meter per second. So it will be a nearly value of 0.66 into 10 to the power minus 19 kg meter. As we are calculating the uncertainty in position, the final unit will be in meter. So this was all about our class. We are basically in a developmental stage of the atomic models. In the later class we will know about the Schrodinger's wave equation and various other forms or various other structure of orbital. Please keep supporting us. Thanks for watching us. Subscribe and share. Thank you.